Let's discuss question number 41 from test 8. This is from fluid mechanics. What is given? A 6 by 6 by 6 cubical tank is half filled with water. The remaining half is filled with oil. And so what is the total force acting on one side of the tank? Okay, so you have a tank which is cubical. So I'm just drawing the front view and half filled with water. So let's start from the bottom. That bottom you have water and then the rest is oil. So what is asked is on one side of the tank, let's take this side, this complete wall, what is the force? Well, this is basically fluid at rest. So because of the hydrostatic because of the hydrostatic pressure, what is the force? That is what is asked. So assuming that here you have atmosphere and you have atmosphere on the right side also, so the atmospheric the force due to the atmospheric pressure, that will cancel up. So we need to just take the gauge pressure, because even if you start with atmospheric pressure here and then go on adding the force, go on adding the pressure, and you take the right hand side, you have only the atmospheric pressure. So basically atmospheric pressure is not taken in hydrostatic calculations, only the gauge pressure is taken. That's what I want to convey. So on this tank, let's draw the pressure diagram on this side of the ball. Starting here, it's 0, and as you know that when you have a fluid at rest and as you move deep into the fluid, due to the weight of the fluid, the pressure increases, right? The pressure increases with the depth. So this is 0, and as I increase, let's come at till the half, it linearly increases rho gh. That's how the pressure varies, pressure increases, it linearly increases with the depth. So rho being the density of the fluid, so this is the pressure here, and this is rho oil gh. Okay, h being this distance. Now, well, if I call the total being h, let's call the total being h. The total is h, then this is h by 2 and this is h by 2. This is the pressure here. Okay, and this pressure will be acting on the wall like this. Now you have the water, so the gradient will be different. Okay, the density of the water is more, because now this is the density of the oil. Density of the oil by density of the water is the specific gravity, which is given as 0.8. So 0.8 density of the oil and density of the water is 1000. So density of the oil would be 800, which is less. So now you have now in addition to this, as you increase, pressure will increase at a faster rate because the density of water is more. So this will just act like this, and the pressure here at the bottom will be rho oil gh by 2, this plus the addition due to water, so that will be rho water g h by 2, because this also is h by 2. So this is the pressure here. So let's now, so this is my pressure diagram, and one important concept in hydrostatic force calculation is that volume of the pressure diagram, the important concept is that volume of the pressure diagram gives the magnitude of the hydrostatic force, is the magnitude, and that is what we want, magnitude of the hydrostatic force. Okay, so how do I now compute this pressure diagram? Well, this is just the front view. Okay, any cross section, if I just take a cross section like this is pressure diagram, and along the depth it will just have the same distribution. It's just like extruded along this depth. Okay, so how do I get the volume of this? Let's first calculate the pressure here and then the pressure here. So let's do it. Okay, so at the interface the pressure is rho oil gh by 2, and that value is 800 into 9.81 hs by 2. So this comes out to be 23544 pascal. So you have to just use a calculator, and the pressure, this bottom pressure will be at the bottom. So this is pressure at the interface, and pressure at the bottom would be rho oil gh by 2, the same thing, plus rho water gh by 2. So this I am just writing out the same thing, 23544 plus water density is 1000, G is 9.81, H is 6 by 2. So this if I add up I'll get 52974 pascals. Okay, so now it's better to, I can compare this area, right? This area is nothing but, so volume I need to compare, volume of this total. So let's first compute this area. That area is half base is this interface pressure, which is 23544, half base into height. Height is 3, which is 6 by 2. So let's write 3. So this is the area. Now this pattern is same throughout the width, right? So width is nothing but 6 because it's sugar. So this is the volume of the top portion of the oil portion, plus the water portion you have a trapezium. So trapezium, let's first compute the area. Area is half, okay, half mean of these two widths. So this is 23544, this interface pressure, plus this pressure is 52974. Okay, so mean of that into this width. This width is 6 by 2, 3, and into the width, perpendicular width, which is 6. So this is what is my total force, total volume of the pressure diagram. So this, if I use calculator, I get close to 9.01 into 10 power 5 Newton, which is close to 900 kilonewton. So let's now look at the option. Option is C. So this is how you systematically, always in a hydrostatic pressure calculation, force calculations, but always I would suggest draw the pressure diagram, compute the volume. Thank you.